So this video is going to be about reaction coordinates. And what's really great about a reaction coordinate is it allows us to combine aspects of thermodynamics and equilibrium and rate and kinetics. So just a quick review, when we think about thermodynamics and equilibrium, if we look at a generic sort of equation here, we can write an equilibrium constant that allows us to relate quantities of products over reactants, and we can use the coefficients from a balanced chemical equation to become exponents in our equilibrium expression, remembering that we do not include pure liquids or solids in our equilibrium expression, so this is particularly relevant in biochemistry that we don't include water. And why this is important for our thermodynamics piece of how much and whether is we can use this thermodynamics equation to relate the spontaneity of a process, delta G, to quantities, or how much. And we highlighted that kinetics is very different from thermodynamics. Kinetics doesn't tell us whether or how much, it tells us how fast a process will occur. So if we take that same chemical equation, now let's not consider it to be an equilibrium because that's pretty complicated. If we consider it to be a one-way reaction, then we have a rate constant, not an equilibrium constant. We can write a rate law such that rate equals that rate constant times the concentration of reactants raised to powers that are what we call reaction orders. And these are not necessarily the balanced coefficients from, or the coefficients from our balanced chemical equation. Rather, these are orders that need to be determined experimentally. But importantly, we do have a free energy parameter that we think about with kinetics, and that's delta G double dagger, and that tells us how fast. Okay, so what we're going to do now is we're going to put these together as we think about how these two pieces talk to one another in a depiction of a process that we call a reaction coordinate or a reaction energy diagram. All right, so how do we draw a reaction coordinate? Well, it basically has axes, and we're going to label these axes as reaction progress and then energy. And we're specifically going to be thinking about free energy for this process. So I'm going to draw here a process that goes downhill in energy, which is what we talked about being a spontaneous process, and that's where the reactants are going to be at a higher energy level than our products. And what we can determine then is the difference between the reactant and product energies is our delta G. So our delta G is again the difference between our final state and our initial state, products minus reactants. So this smaller number subtracting a larger number from that is going to give us a negative value. So specifically for this case, the sign of our delta G value is going to be important. I'm going to slide my stuff over here just a little bit to give me some more room. The sign of that is going to become important because as we see here, it is a negative, and that tells us that our reaction is spontaneous. If it was a positive, then it would be non-spontaneous. But here, with the reaction energy diagram that I've depicted here, this is a spontaneous process. Okay, so this is the weather part of our thermodynamics piece. When we think about the how much part, this has to do with the magnitude that we have for that delta G value. So that magnitude is going to tell us how much product we make, and so the larger the value is, and we get this again from our equation, delta G equals minus RT ln of KEQ. Okay, so those are the pieces that we get, and I really haven't even fully drawn my reaction coordinate here because it's important to highlight that we just don't have our reactants slide down the slope here and go to products. They actually need to go through an energy barrier, an activation energy, to get from reactants to products. So what I'm going to draw here is I'm going to draw a hill that our reactants need to go up and over to come down on the other side and become products. So a few other pieces to label here. We can label this peak up here TS, which stands for transition state. So TS is the transition state. And what that represents is a hypothetical interaction of a reactant species where bonds are simultaneously breaking and forming as they transition between the reactant state to the product state. So just like you can imagine a ball not being able to sit at the top of the hill, but rather go to either side of these energy minima, if you will, the same is true with the transition state. We don't have molecules kind of exist as transition states. But transition states are really important because one piece that we'll get to later that we learn about with transition states is they are very useful for drug design. A lot of drugs, because they will bind very tightly to and inhibit enzymes, have structures that resemble the transition states for reactants being converted to products in certain enzymatic reactions. Okay, so the last piece that I want to label on here is this energy difference. So what we're really labeling is energy differences on this diagram. We're always going to be looking at energy differences between two stable species, and that's going to give a delta G value. Or in this case, when we look at the energy difference between a stable species and the transition state that's immediately adjacent to it, we call this a delta G double dagger. This is our activation energy. And importantly, this activation energy, now we're not going to have a sign for it, it's always going to be positive, but the magnitude of this is going to tell us how fast. So the magnitude is going to tell us the speed of the reaction. Okay, so this is where we get our how fast. So just kind of summing up here, okay, a reaction coordinate is a great way to show how reactants transition to products. The difference between reactant and product energy levels is going to give us delta G. That's a thermodynamic parameter that's going to tell us whether a process occurs. And again, if we go downhill, that means our delta G is going to be negative, and that is a spontaneous process. So yes, it occurs. And the magnitude of delta G, how large this arrow is going to tell us how much, because the magnitude, the value of that delta G, is going to be directly related to the equilibrium constant. On the other side here, we have an arrow that's always going to be a positive value, and the height of that arrow is going to tell us or reflect the speed of the reaction. The larger that activation energy, the slower our reaction is going to be. So this is a kinetics parameter, or related to kinetics, in telling us how fast a reaction occurs. So we're going to tie this all together with a beautiful example here to think about how ATP works in your body. So that's our last slide that we're going to have here, is we're going to think about ATP hydrolysis. So just a little bit of a review here. If we've got ATP reacting with water, that's going to hydrolyze it into ADP and our inorganic phosphate, reminding ourselves that PI is inorganic phosphate. Okay, PO4 3-. We know that ATP is your biological money. And so the question is, how is this money used in your body? How valuable is it? How stable is it? And we can use a reaction coordinate to kind of explain and answer all of those questions. So I'm going to zoom in down here, because I'm going to actually have a very small reaction coordinate that I'm going to draw here, and you'll see why in a minute. So we're going to draw a reaction coordinate here that's going to show our reaction progress. And then we're going to have our free energy sort of plotted here on our y-axis. Move this over just a little bit here. Okay, and so our reactants here, our ATP, I'm not going to include water, because even though it is a reactant, when we consider equilibrium constants, we wouldn't put water in there. And it's hydrolyzed to ADP and PI. We know that it's a downhill process because we know that we get energy out when we hydrolyze ATP. And we actually can define exactly how much this is. So this delta G is going to be negative. Delta G is going to be negative here, and it's going to be, let's see, this is going to be equal to, it's going to be equal to minus 30.5 kilojoules per mole. So that is a number that I want you to know. That's an important number. That is the value, the cash value, if you will, of ATP. And so when we want to think about our ATP money, okay, we know that our money, our ATP, is valuable because it has a significant large negative delta G value when we consider its spending, its hydrolysis, if you will. Okay, so 3 questions we're going to answer here. The first we've answered with delta G. We know that our money is valuable. Okay, so why I have a giant reaction coordinate here is we're going to answer the second question here, which is how stable is our money? Here is how we define how stable our money is. When we consider reaction coordinate for ATP hydrolysis, we have a huge activation energy barrier. So this, and I'm being very exaggerating with this, this is a very large delta G double dagger. Okay, so this large delta G double dagger it tells us that just ATP sitting around and spontaneously combusting or hydrolyzing into ADP and PI does not happen readily. The frequency with which ATP by itself can come up and over this barrier and get spent is pretty infrequent. Okay, so what this tells us is that our money is stable. But the question is we've got money in our pocket that's valuable, it's stable, but the third piece is how do we access it? And this is where we understand that if we wanted to access this money, what we really want to be able to do is take the height of this transition state, the height of that hill, and make it smaller. If we only had this high of a hill to go up and over, we could get at our money quite easily. That's exactly how enzymes work. So how do we access our money? It's our third question. So how to access our money? The question is answered by the use of enzymes. So here's how enzymes work. Enzymes will bind to and stabilize the transition state, and they will thus decrease delta G double dagger and make our reaction faster. So enzymes bind to and stabilize the transition state. And in doing so, they decrease our delta G double dagger. So when we make that delta G double dagger smaller, this is going to make our reaction faster. But it's very important to highlight here that kinetics and thermodynamics are different. So while enzymes decrease and stabilize the transition state and make our delta G double dagger smaller, they do not affect delta G. So there is no effect on delta G. And 2 things are kind of a result then of that. There's no effect on how much product we make and no effect on whether that process happens. So there's no effect on delta G, so it does not make more product, and it does not make a non-spontaneous reaction spontaneous. Said another way, when we decrease this energy and we have an easier time getting up and over this hill, we just get to this predetermined amount of product faster. So we don't change the amount of product that we make. And if, for example, this was an uphill reaction, it was a non-spontaneous reaction, enzymes will not make a non-spontaneous reaction spontaneous. So I know this was a little bit longer of a video, kind of reviewing thermodynamics and kinetics, and importantly, highlight how they all come together with a reaction coordinate.